Our first speaker will be Bob Austin.
Thank you. Okay, so I'm talking about the Quarry Cluster approach, which we've used in Florida for quite some time. And the visual approach to identifying Chert provenance has sometimes received a bad rap because of the presumed inaccuracy when compared to instrumental techniques. So I don't know if you looked at your schedule, but I've added this tagline to my title up there to emphasize the fact that while the approach may be an old story, it's actually the best story we have in Florida for examining a variety of archaeological questions involving the procurement, transport, and use of Chert. Furthermore, its accuracy and reliability are greater than many people realize, and these continue to improve as more refinements are made. Its ease of use, low cost, and ability to characterize large samples when compared to less available and more costly techniques ensures that it will continue to be used well into the foreseeable future, particularly in cultural resource management, which is where I come from, where costs and schedules are paramount concerns. Okay. Let's try this. There we go. So the Quarry Cluster concept was developed in the early 1980s by geologist Sam Upchurch and colleagues as a way to visually assign lithic artifacts to geographic localities where Chert outcrops share similar geologic characteristics. Characterizing different rock types and inferring provenance using visual attributes has a long history in both geology and archaeology. Geologists use them to characterize and correlate biostratigraphic units over large geographic expanses. In Florida, the presence of certain fossils and other inclusions characterize the major geological formations, including those that are known to contain Chert. When used in archaeology to infer Chert provenance, the visual approach works best when source locations are geographically restricted and the attributes associated with these Cherts are visually distinct enough to distinguish them from one another. When these conditions are not met, the ability to accurately and consistently infer provenance visually diminishes. To explain how we use the method in Florida, I need to provide a bit of geological background. The different geological strata that contain Chert deposits that were available to prehistoric people are shown on the right in this slide. They include the Eocene Aucilla limestone, the Oligocene Suwannee limestone, the early Miocene Tampa member of the Arcadia Formation in central Florida, and the St. Marks Formation in North Florida, and the Middle Miocene Hawthorne Group formations such as the Peace River, Alachua, and Statenville. Now it doesn't want to do that. Technologically challenged. Within these formations are two types of Chert. The first is associated with the Miocene Hawthorne group of sediments that includes beds of clay with opaline diatoms and other microfossils. Intermixed with the Hawthorne sediments and formed soon after their deposition are deposits of opal. These formed when silica-rich fluids filled cracks and voids in the Hawthorne clays. The appearance of this opaline material is very distinctive. It's lustrous. It's almost greasy looking when in hand sample and contains abundant quartz sand, phosphate pellets, and occasional fossils. And that little white circle on there kind of highlights a phosphate pellet in that piece of Chert. Major source areas are the Peace River, Alapaha, and Swift Creek quarry clusters. These clusters sometimes also contain replaced dolosilts and silicified oysters. Opaline Cherts occur sporadically in other clusters as well. By far the most common type of Chert in Florida and the southeastern coastal plain is silicified limestone. The post-Miocene weathering of the Hawthorne opaline sediments resulted in replacement and void filling of the underlying early Miocene, Oligocene, and Eocene limestone deposits by silica-enriched fluids. The fluids percolating down through the silica-rich Miocene clays is what silicified the underlying limestones. If the silicified limestone is near land surface, removal of the cover sediments via fluvial or marine erosion and or sinkhole development was all that was needed for Chert to become exposed and available for procurement. Upchurch and et al. Investigated a number of geochemical and petrological methods for determining chert provenance, but use of geochemical criteria proved inconclusive because all the lissified limestones in primary chert deposits were deposited under similar tectonic and sedimentologic conditions. The exception was the opaline cherts, which represent a different sedimentary origin, but these cherts are also easily identified visually. For the silica-replaced limestone cherts, textural and paleontologic criteria were found to be the best tools for determining chert provenance. The limestone strata were deposited under different regional hydrodynamic and diagenetic regimes, and their fossil content varied with the age of the deposit and the depositional environment. Therefore, the chert that formed by replacement of these limestone strata by silica can be differentiated on the basis of their textural and fossil content using visual and non-destructive means. Now, here are some examples of replacement cherts from different geologic strata. The Eocene age Aucilla cherts are perhaps the easiest to identify because of the characteristic grainstone to packstone fabric, which just means that the grains, in this case fossils, are very closely bound together. And the abundant foraminifera tests that are visible in even small flakes. The most common and diagnostic of those are the genus Lepidocyclina, which is shown here, but nummulites are also present in some cherts. Pectin molds are another common fossil. Quartz sand inclusions are very rare to non-existent, and the quarry clusters that contain Aucilla cherts are distinguished primarily on the size and the abundance of the orbitoids between the clusters. Swanee limestone cherts are characterized by their grainstone fabric, small fossils, particularly melialids, the presence of quartz sand, and echinoid fragments. These last consist of calcite fragments that are easily visible in fresh samples, but most archaeological examples that have been exposed to acidic soil conditions no longer contain calcite because it's weathered out. What remains are the small rectangular voids where the calcite originally existed. Fossil size, amount of sand inclusions, amount of secondary porosity, and to a certain extent color are the primary features used to discriminate quarry clusters containing Swanee cherts. Cherts formed in the Tampa member of the Arcadia Formation and its equivalent in northern Florida, the St. Marks Formation, are perhaps the most variable in terms of their visual attributes. The parent limestones were formed during the early Miocene when sea level varied and both marine and terrestrial sediments were deposited. In general, Tampa St. Mark's cherts are characterized by common to abundant foraminifera of the Peneropelid family, usually in a packstone to waxstone fabric. Again, they're not as closely clustered together. And rare to abundant quartz sand, with sand being more common in the St. Mark's cherts than in the Tampa cherts. Also present are plesiopod tests, in other words, little bivalves, palatal material, coral fragments, rock fragments, and brecciation. And some cherts are basically mudstones with very few inclusions. So we're lucky here in Florida that the various chert-bearing formations are geographically restricted to the crest and flanks of the Aucilla platform and the Chattahoochee Arch. Just as important, these formations are differentially exposed at decreasing elevations from west to east and north to south, as a result of sea level variation through time, as well as erosion during and after the Miocene, and possible isostatic uplift during the Miocene. This means that, in general, cherts associated with the Eocene age Aucilla limestone occur on the crests of the arches. Swanee limestone cherts are more present on the flanks of the arches, and cherts of the Tampa St. Mark's limestones are restricted to the southwest and northwest. Thus, identifying a specimen to its parent formation is relatively easy and provides a moderately high degree of geographic specificity in terms of possible source locations. In other words, it's basically a lot easier to assign an artifact to a geological formation and where it outcrops simply because of the fossil and other inclusions that are so distinct between those formations. A quarry cluster, however, is more specific. Make sure I didn't have to do that. Okay. A quarry cluster, however, is more specific and is defined as a geographic area where, 1, silicification of texturally and paleontologically similar cherts occur, 2, the chert was buried by sediment thin enough for outcrops to become exposed over time, and 3, fluvial, marine, and karst processes were active, providing access to the chert. The first criterion focused on the interformational variation in chert attributes, and the last two are related to exposure and availability for native peoples. Therefore, the goal of chert provenance using the quarry cluster concept is to assign artifacts to an area of origin rather than specific quarry or localized outcrops. While a locality attribution is in some cases possible, the area approach has proven to be reliable and robust. Now, a mistake that we see often in Florida's archaeological literature is the tendency to refer to cherts from different quarry clusters as different types of chert, and this really isn't accurate. A quarry cluster is a geographic area within which chert outcrops tend to share a suite of attributes. Now, there may well be intra-cluster and intra-formational variability in attributes that enable one to identify a type of chert, and I'm going to discuss a few of those in a minute, but quarry cluster is not a type. This is a subtle but important distinction because the term type carries with it some connotations related to identification, locality, napping qualities, and subsequent archaeological interpretations that may not be supportable. So, to repeat, remember this. The assignment of chert artifacts to a quarry cluster simply means that they exhibit attributes that enable assignment to a geographic area. They do not necessarily represent a type of chert. Now, I mentioned that some chert types have been recognized, and this is especially true among the Tampa limestone cherts because they exhibit a lot of variability in terms of composition. And this has allowed us to identify some specific type of cherts that crop out in geographically restricted areas within the Hillsborough River and Caladesi quarry clusters. Here's an example of a fossiliferous chert with abundant coarse coral and coral gel fossils, palatal material, and forams, and this material is common at archaeological sites around Tampa Bay. It's known locally as Bay Bottom chert, and it frequently occurs in Paleo-Indian through Middle Archaic artifact assemblages. There's only one known terrestrial source location for Bay Bottom that's been identified, and that's on Rocky Creek near Old Tampa Bay, and that's the dark-colored little blob there at the top of Old Tampa Bay. Where it is found archaeologically, the material is mostly in the form of work tools, with few waste flakes or cores. It's much less common in post-Middle Archaic assemblages, and when it does occur, it's in the form of scavenged and recycled artifacts. So based on these observations, it's been inferred that the source of this chert became inaccessible during the Middle Miocene to late Archaic, the Middle to late Archaic, due to early Holocene sea level rise, and that the source locations likely are now submerged in Tampa Bay, where a well-developed river-cut valley is located. Both Bay Bottom and Hawthorne group cherts have been found in submerged exposures there, and the cherts were likely exposed by erosion in the channel of the Paleo River. Although widespread, cherts composed of fossiliferous packstones and waxstones tend to be concentrated in outcrops around Tampa Bay and along the Gulf Coast of Pinellas County. Pentaropelid forams are common, and the cherts also contain moderate to abundant quartz sand inclusions. So this type of chert is present in both the Hillsborough River and the Caladesi River quarry cluster. So some chert types can cross-cut quarry clusters, another reason for making that distinction. Several outcrops near Caladesi Island and the mouth of the Anclote River in northern Pinellas County are characterized by cherts that have a mottled or brecciated appearance, a dark gray color on fresh surfaces, and again, common pentaropelid fossils. The chert fabric is a micromosaic quartz, and it commonly develops a characteristic grayish blue patina, which you can see on the example in the bottom. And here, the one on the bottom, you can see the dark colored chert on the interior, and then the weathering rind, the lighter color weathering rind, and then the gray-blue patina on the exterior. Yet another specific type of chert is found only in the upper Hillsborough River region, particularly along one of the tributaries, Cowhouse Creek. This chert is characterized by the presence of charophytes, which are freshwater algae, and their oogonia, which are the female reproductive apparatus. I didn't know any of this until I got into chert. The Cowhouse Creek region of the Hillsborough River Quarry Cluster is the only currently known source area for this particular type of chert. Here you can see a late archaic hafted scraper, and it contains charophytes and was recovered from Weeden Island, which is on the west side of Tampa Bay. And so the straight line distance to the source area for this chert is about 25 to 30 kilometers from Weeden Island, although they probably went around the peninsula there and up into Old Hillsborough Bay and then straight up the Hillsborough River. Ongoing efforts to improve the quarry cluster approach have focused on refining the geographic boundaries of existing quarry clusters and the visual criteria used to characterize them, and on identifying and mapping previously unrecorded quarries and outcrops, particularly in quarry clusters that were underrepresented in Upchurch et al.'s original formulation. For example, John Endonino sampled a number of locations within and near the Gainesville, Ocala, and Lake Panasoffkee clusters in central Florida, which are characterized by cherts formed in the Ocala limestone. Upchurch et al. Originally indicated that cherts from these quarry clusters could be distinguished by the size and abundance of diagnostic orbitoid fossil tests, but operationalizing these criteria was largely subjective. John was able to quantify these differences, reconfirming that size and abundance are reliable as the primary criteria for separating and visualizing or visually identifying these three quarry clusters. Based on his size and abundance data, basically he counted and measured all the orbitoids in all of his samples. The geographic extents of the three quarry clusters were revised. Furthermore, the Lake Panasoffkee quarry cluster was further subdivided based on the abundance of orbitoids into Lake Panasoffkee East, which has fewer, and Lake Panasoffkee West, which has more. I was able to expand the boundaries of the Peace River quarry cluster based on survey of chert exposures in the river. I also identified opaline chert outcrops along the Alafia River near Tampa Bay. Oops. There we go. And archaeological projects in the Peace River Valley have identified a wider variety of opaline cherts than was previously known for this cluster. In addition to opaline cherts and silica replacements of Miocene dolosilts, limited exposures of Tampa limestone cherts also have been identified along the Peace River. Recent investigations along the Santa Fe River by Brent Wiseman and myself have identified numerous chert sources derived from residual Swanee limestone boulders. The rivers within Sam's original Santa Fe quarry cluster, which he originally was thought to contain cherts from the Ocala limestone based on very limited sampling. Ocala cherts are present, but they appear to be restricted to the western part of the quarry cluster where the Santa Fe and Ishnatucknee rivers merge. Adam Burke, up at the top there, has been surveying the Swanee River in the White Springs quarry cluster and has identified several new chert and coral quarries and outcrops. And then Jim Dunbar and his colleagues have identified several chert exposures in prehistoric quarries in inundated. Damn. Yeah, I need some water. Where am I? Oh yeah, in the northeastern Gulf of Mexico. And those appear to be mostly in Swanee and Ocala outcrops. jumping ahead here, but I'll mention more work that Adam has done, which is conducting research to determine if instrumental techniques can be successful in assigning artifacts to known quarry locations. And that's what he's going to be talking about after this presentation. And then Bob Bowers and Rob Tycat at the University of South Florida have recently presented data indicating that it may be possible to use UV fluorescence to characterize cherts from different quarry clusters, even if it proves to be successful, or even if it proves to be successful, might be a relatively inexpensive way to check assignments based on the visual method. Of course, new outcrops and quarries are being discovered and documented all the time within all of the various quarry clusters. And all of this work is helping us to refine the nature and extent of the original quarry clusters and is strengthening our ability to assign artifacts to specific quarry clusters. Now, this slide. One of the types of raw material that's been very difficult for us to associate with specific quarry clusters is silicified coral. And coral of the genus Siderastrea, which is shown at the top there, was used most often for making tools. Other corals sometimes were used, but Siderastrea was preferred. These corals grew in large colonies in the Oligocene and Miocene seas that covered Florida. Because of its structure, silicified coral is very difficult to flake without the use of thermal alteration. It's no coincidence that the significant increase in the use of thermal alteration during the Middle Archaic period in Florida also corresponds with a similar increase in the use of silicified coral. A major source for silicified coral is the uplands of central Florida, where extensive quarries of this material are present in erosional creek banks and sinkholes within the upper Withlacoochee River quarry cluster. Another major coral source is White Springs quarry clusters in northern Florida. Coral-bearing strata crop out in other parts of the state as well, but it's extremely difficult to assign coral artifacts to specific quarry clusters because of the dominant use of a single genus for toolstone, the difficulty of identifying coral species in well-silicified artifacts, which tend to obliterate their structure, and the geochemical similarities of the various outcrops. Now, John Bryan, a geologist at Northwest Florida State College and an expert on coral, has been working with us to better identify the corals being used for toolstone, their geological occurrence and distribution, and potential source locations. In terms of applications, the quarry cluster method has been used to identify Chert provenance at archaeological sites of all time periods, from the Paleo-Indian through the Mississippian. And based on these studies, there are some general statements that we can make regarding Chert procurement. Perhaps not surprisingly, where Chert sources were common, there was a dependence on mostly local sources. And this is true, again, all through time. And it's true regardless of archaeological period. For example, at the Genie's Betterback site, which is an early archaic Boland site located near the Swanee River, raw material analysis of a large sample of tools and debitage indicated that the occupants obtained nearly all of their lithic resources from sources located within 30 kilometers of the site, although about less than 1% came from as far away as Tampa Bay. A similar focus on local Chert sources was identified both for the Paleo-Indian and early archaic components at Harney Flats, where all of the tools and debitage examined there were made from stone obtainable from sources in the near vicinity of the site. Similar results have been reported for later period sites also. Rich Estabrook documented use of nearby Swanee limestone Cherts from the Brooksville Quarry Cluster at the Woodland period Crystal River site. My own work at Weeden Island and Safety Harbor sites in the Tampa Bay region indicate primary dependence on nearby sources I'm out of a paper here. Okay, well, basically, they were found to be, I need a new set of glasses. Primary dependence on nearby sources within the the Hillsborough River and the Turtle Craw Point and the Caladesi Quarry Cluster. So even in that area, late period sites tend to focus on local resources. In addition to looking at mobility and procurement strategies, the Quarry Cluster method has been used to address social questions related to ritual, group aggregation, and social control of resources. I have to move ahead here. At Fort Center near Lake Okeechobee, several large hafted bifaces made of chert obtained from the farthest source area, the Lake Panosofsky Quarry Cluster, which is over 200 kilometers away, were found exclusively at Mound A and were used for cutting, scraping, and incising. Mound A is believed to have been a residence for ritual specialists, and the bifaces may have been used to produce the elaborate wood carvings found in the adjacent mortuary pond. Archaic stem bifaces of thermally altered silicified coral were found in the nearby Mound B burial mound and the mortuary pound. Some were ritually broken or modified by grinding. The archaic points were either scavenged from earlier sites or obtained through exchange. Now, I've argued that the use of stone that was both geographically and temporally, in the case of the archaic artifacts, conferred enhanced ritual value on these implements that contributed to their value and use in ritual activities. Rich Estabrook's analysis of chert artifacts from Crystal River tested several hypotheses related to social inequality. One hypothesis stated that if social inequalities existed, social elites may have had access to or controlled specific quarry locations. His raw material analysis failed to support this hypothesis, indicating a lack of preference for cherts from different quarry clusters within the site. Now, there's no question that the quarry cluster approach is not perfect. The problems that have been encountered, such as boundary identification, quarry clusters that contain cherts with characteristics that are similar to other quarry clusters of the same geological formation, and the difficulty of distinguishing quarry clusters geochemically, continue to be the focus of active research. Some problems are inherent in the method itself. Small artifact size, surface weathering of patina, or an absence of identifying inclusions inhibit the ability to identify those attributes that enable quarry cluster assignment. It's not uncommon to have anywhere from 5 to 20% of the specimens in a large collection assigned to the indeterminate category because of these limitations. On the other hand, these problems are offset by the ease of the method's application, which has led to its widespread use, and the ability to analyze large samples of artifacts from sites, including debitage as well as tools. And this is extremely important, in my view, for ensuring that less common quarry clusters are identified in assemblages, as they may be the artifacts that enable documentation of trade and mobility patterns, as well as temporal patterns in the use of different clusters and chert types. Many of the early successes in the use of instrumental techniques were limited to differentiating chert sources that have very different geological origins. Although new analysis methods are producing some encouraging results, it remains unclear how effective instrumental techniques will be when geological origins are so similar as among the coastal plain limestones. Even if they do prove to be successful, cost, availability, and turnaround time for results will continue to limit their use to verifying assignments based on the visual method, at least for the foreseeable future. Consequently, I don't see the visual approach going away anytime soon, and because of that, it's incumbent on those of us who use it to continue to refine and make it better. And I want to thank Jim and ARI for inviting me to be here, and all of my various co-conspirators who have contributed as much as I have to this research, and especially Sam Upchurch, who's been just a great mentor and friend to all of us. So thank you very much.